With halogenoalkane reactions, it's easy to know what you need to add up here if you think about it a little bit more deeply. So if you're trying to get a CN on the other side, you obviously need to add a CN over here. And so the other thing that's a little bit more difficult is working out whether it needs reflux or not. And so you need to understand that the boiling point of these two things are quite different. And so that one's 12 and that one's 97. Now, how would you have known that? It's actually quite difficult, and it sort of highlights, this one's a great molecule for highlighting the flaws in us teaching you what is a polar and non-polar molecule. So we teach you that the electronegativity difference, if it's a polar bond, actually this one is less electronegative, and also molecular weight, and this one is actually lighter as well. So it makes no sense, and it's asymmetrical, but they're both similarly asymmetrical. And so this is only between two atoms here. It's a single bond. And we've actually got a triple bond here, so that system sort of fails as far as there's a polar bond is concerned. And so what you need to do is actually take a much better definition, because symmetry is a bit of a vague term, and electronegativity difference doesn't always work. So the physicists actually do the forces and do a dipole moment. So they add up all the forces plus direction, and they give you a true accurate definition of the differences in positive and negative. And so using dipole moments, which is probably the only way and the definitive way of really knowing if it's a polar molecule or not, these dipole moment numbers, I haven't put units there, are the real differences in the real polarity. So you can see that the triple bond, the effect of that is to give you a much, much more polar molecule. So even though the year 11 definition is a fail here because the molecular weights are lower and the electronegative difference is also lower, the true polarity of the molecule is shown by dipole moments, and this one is much, much higher. And so that is why we have to use reflux, because typically you can also imply that there's heat, and you can also imply there's probably a difference around room temperature, because we're heating it up to get it to react and heating it up to separate. And so what you've got here, the reason it's not enclosed, which would be nice, is because there'll be a build-up of pressure, and this will pop up and smash the lights, and glass will go everywhere, like I saw someone do in first year chem at uni once, which was quite exciting. We all wondered, well, how the hell did you do that? And that's what they did. They put a lid on there. And so hopefully this is very, very cold. It's going to have to be cooled water, because it's got to be a lot less than 12. Get it back to a liquid and get it back into this system. So that is the reason why there's reflux, in order to get the reaction to work. The last thing I need to talk about is ethanol. Now, water, if you put it in water, the OH groups react quite easily here, which we'll show in the third slide. Whereas with ethanol, it's far less reactive. And so they're the reasons for those things here, and hopefully that will help you remember halogenoalkanes with cyanide turned to nitriles. Now this one here is of a similar vein, but it's much, much easier to tell that this has a much higher melting boiling point, because there's hydrogen bonds there, so hydrogen bound to N, O, or F. And so that makes life a lot easier. Again, you're trying to get ammonia to an halogenoalkane to an amine, so of course you've got to get the ammonia from somewhere, so you add it. Same story, you don't want an alcohol to form, so you have to do it in ethanol, and as I've mentioned before, the heat and reflux based on the boiling points. So going to this one here, I'm not going to go into secondary halogenoalkanes. They'll do both. Just explaining here, where are we? That carbon's only bound to 1 or none, so that's a primary, and the carbon that's bound to the halogenoalkane here is bound to 3 different carbons, so that's a tertiary. Okay, so then we get different reactions for that. So as I said before, if you do put it in water, the water will react. So if I can find my pen, this negative dipole moment here, and there's a positive one here, and a negative one here, and a positive one here. And so this here will come over into here, and this will push out and join out to the sodium to become sodium chloride, and the OH group here will come along here and it will form an alcohol. So this is substitution. You're taking out the chlorine and adding the OH. It's in aqueous, that's why it works. The sodium hydroxide helps with this reaction, and of course they're both reflux. Now, if you've got a tertiary, this doesn't work very well because there's steric hindrance. So if you're trying to get this elimination reaction here, you're going to put it in ethanol because you don't want any accidental side reactions of alcohol. You're also going to just have, it's a very slow reaction, you just have to wait for this to pop off, basically. So the NaOH is a catalyst for that, and what you're going to get is you're going to get a double bond form. So this is reflux and only for tertiary reactions. And so the OH from the NaOH takes a hydrogen out. So here we have, let's just say it's this one here that ends up being reacted. You can see that there's one less hydrogen. So the hydrogens come out, reacted with our OH to become water, and the Cl's popped off, attracted to the Na, and there we get a elimination reaction. Lastly is halogenoalkane reactions with halogens. Now, it's not the bond enthalpy that matters. These numbers are not too different anyway. These here, it's all about positive and negative interactions. So this one here, if it's higher up on the periodic table, it's more electronegative, it's going to have more of a polar bond. So you can see chlorine is higher than iodine. And so this is far more negative, and this is far more positive than this situation that it becomes. And so it's much more open to attack. So we call that nucleophilic attack, electrophilic attack. So things that are negative are going to want to come in here. Things that are positive are going to want to come in here. And that's just complicated words to describe positive is attracted to negative. So the more polar it is, the more likely it is to cause an attraction and therefore react. Again, all of these are in ethanol, unless of course you want the alcohol.